An artillery shell erupting from a cannon barrel presents a specific challenge for kinematics. It travels forward at hundreds of meters per second while simultaneously spinning at high frequency along its longitudinal axis. Irodov problem 1.45 asks us to quantify this relationship. We are given a barrel length of 2 meters, a final velocity of 320 meters per second, and 2 internal turns. Our objective is to determine the final angular velocity, omega, at the exact moment of escape. Analyzing this coupled motion as a single system is difficult. To simplify the math, we will untangle the physics into 2 independent, manageable tracks. This strategy provides a reusable framework for any complex kinematics problem. By isolating the individual components of motion, we can use simple relationships to solve for a sophisticated result. We begin by inventorying our known variables: the barrel length, the exit velocity, and the number of rotations. Before applying our equations, we must standardize our units. Specifically, the turns of the shell need to be expressed as a continuous angle for our rotational formulas to function. One complete rotation traces out exactly 2 pi radians. Since our shell undergoes n turns, the total angle covered, phi, is 2 pi multiplied by n. For this specific problem, that gives us an angular displacement of 4 pi radians. Converting units at the very start of the process prevents the small cascading mathematical errors that often derail a complex calculation later on. We will focus first on the linear world. For this stage of the analysis, we look purely at the forward translation and ignore the spin entirely. The shell starts at rest and undergoes uniform acceleration until it reaches its final exit velocity, v. Rather than calculating the acceleration directly, we can use a shortcut, average velocity. Since the acceleration is constant, the average speed over the total distance is simply halfway between 0 and the final velocity, which is v over 2. We know that distance is the product of average velocity and time. In this system, our distance is the barrel length, L. Rearranging this to solve for the duration of the event, we find that time equals twice the distance divided by the velocity. Using the average velocity shortcut illustrates a broader principle. The most efficient path in physics involves simplifying the motion before you start the algebra. Now we pivot to the rotational track. This view isolates the spinning motion as if rotating in a fixed position. Just like linear motion, the spin starts at 0 and increases steadily until it reaches its final angular velocity, omega. We can apply the exact same average velocity logic to this rotation. The average angular velocity is halfway between the start and the finish, or simply omega over 2. The total angle the shell rotates through is equal to this average spin rate multiplied by the time spent in the barrel. Substituting our earlier conversion of 2 pi times n for the angle, we get our second time equation. Time equals 4 pi times n divided by omega. Rotational kinematics is a mirror image of linear kinematics. Recognizing these patterns lets you apply the exact same logical steps to completely different physical systems. We now have 2 separate equations for time. Because they describe the same event, they share a single constraint. The shell spends the exact same time spinning as it does moving forward. This makes the variable t the bridge between our linear and rotational tracks. By setting our 2 isolated time expressions equal to one another, we form a single master equation. Now we solve for our target variable. Rearranging to isolate omega, we find that the final angular velocity equals 2 pi times the turns and the velocity divided by the barrel length. With the algebraic work complete, we plug in our initial values: 2 turns, 320 meters per second, and a 2-meter barrel. The 2-meter barrel length in the denominator cancels out with the 2-meter rotation variable in the numerator, leaving us with 640 multiplied by pi. Isolating a shared variable, like time, coordinates these 2 distinct systems. By finding the one thing they both have in common, we can solve for a rotational unknown using linear data. Multiplying our result by pi gives us a raw value of approximately 2010 radians per second. Since our input data was provided to 2 significant figures, we must round our final result accordingly. This leaves us with 2.0 times 10 to the third radians per second. Before we conclude, we should look back at our final algebraic formula to see if it accurately reflects physical reality. Our formula shows that a higher linear velocity, or more internal turns, would increase the final spin. Conversely, a longer barrel would decrease it. This logic matches our physical intuition. Mastery in physics is not just about calculating a final number.
It is about deriving algebraic relationships that prove you understand how the physical world works. Keep practicing, and I'll see you in the next problem.